Good morning, ladies and gentlemen. We are going to start off by hanging a 200-gram mass on the spring and letting it rest at equilibrium. Measure and record data.
So you should record this in your journal.
So we want to measure and record the height.
Or your notes,
Okay,
I should say.
so-
Don't.
Is that right there?
That's equilibrium
Oh,
right
perfect.
there.
That's 200 grams.
Yeah.
Okay, here we go.
So
That's
we
right.
want to measure the height.
Okay, I'm going to have a hard time seeing this right here.
What do you want to call that, boys and girls?
Maybe
24.2. 24.2. Yeah, we'll call it 24.2
Okay.
centimeters. So that's equilibrium. That's where the force of the spring up is balanced by the force of gravity down. And we got 200 grams plus 25, that's 225 grams or 0.225 kilograms.
Yeah, we'll say mass equals 0.2. Wait, how much is it?
It's 220, well, we got 25 grams is the pan, plus 200 is 225 grams. That's 0.225 kilograms.
Yeah, directions say 200 grams, but it is what it is.
Here, let's just,
Oh, thank you, sir. Okay, all right. Oh, and Boykin, do we want to change this to meters yet, or do we just want to hang on to it?
no, let's just leave it at centimeters.
Okay. All right. Start the mass oscillating and estimate the time. The height at the lowest point. What is the amplitude report? Okay.
Okay, so you just kind of,
I'm gonna try to as best I can. There we go. Not bad.
all right, we're gonna have to estimate here.
Okay, I'm gonna need your guys' help. So, right there.
Yeah, it's about 21 centimeters.
Okay. So lowest.
Low is 21 centimeters.
Okay.
Now, what's the definition of amplitude? See, because it says, what's the amplitude?
Yeah. So if my equilibrium is this middle part and the lowest is down here, the amplitude is however far it is from the equilibrium.
Maximum displacement from equilibrium.
So we could just subtract those two, right?
Yeah, I think it's going to be,
What is that?
amplitude is going to be 3.2, isn't it?
3.2. Is that right?
Yeah, 24 minus 21.
Well, that 21. Oh, I got that two right there.
Yeah. Well, and you know, for significant digits, you can see the uncertainty. It was hard to tell exactly where this was. It was also hard to tell where this was. We'll call it 3.2.
You want to call it 3.2? Is
Yeah.
that easy? All right. So that is our amplitude. So amplitude equals 3.2 centimeters.
Uh-huh.
Sweet. So you should have this data written down, ladies and gentlemen. Okay.
Now,
Okay. So now we want to measure the time for 10 cycles. Ooh, so it would have been good if I kept it going, huh?
well, it's going to be the same. It'll have a different amplitude, but
Yeah.
the period, the frequency, the time for 10 cycles has nothing to do with amplitude.
Oh, on. I'm like, start. Read.
So give it a little.
Okay, so for 10 cycles, and we're gonna start when it goes to the bottom, right? So, and 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Boom. Okay.
So the time for 10 cycles.
I got 6.96
so
seconds.
T10.
6.96 seconds. And then, what is the period?
Period is the time for one cycle.
Okay, so I can just divide this by 10.
The time for 10 cycles.
to get my period, right?
Yep.
So 6.96 divided by 10. And what do I get? I know, Miss.
Thank God for calculators.
Seconds per, I guess per cycle.
So
It's early.
that's 0.696 seconds per cycle. Okay, next question.
What is the frequency?
What's the relationship between the period and the frequency?
Well, we know that they have an inverse relationship, right?
Yeah,
So can't we just take this number and we can flip it, right?
yeah,
Because frequency equals 1 over the t, over
Yeah.
the period. So 1 divided by that answer, and I get 1.44
1.44
hertz.
cycles per second.
Okay. It hurts you, no?
Yeah, you put down cycles per second because it tells you this is 1.44 cycles every second.
Dang. Okay, so a little over 1, right?
Yeah, it is also hertz, but
Okay.
seconds per cycle and cycles per second, it's really important that you've got units that let you see what the heck's going on.
All right, what is next?
Wow!
Okay. Are we done here, Boykin?
Yes, we are.
Okay. Let's rock and roll.
Yeah, I
Okay,
think-
this should look familiar, yes?
Yeah. So what does this omega over here stand for?
So this is angular frequency.
Yep, it was angular velocity for angular motion, but this isn't really angular motion, it's simple harmonic motion. So
Yeah.
this is angular frequency.
And if you guys remember that video yesterday, it showed you a picture of that shadow going up and down.
Yeah.
And what was causing that? Well, it was that angular motion, but in terms of the shadow, you get simple harmonic motion.
Ooh, I just had an idea.
Yeah.
Girls find the angular frequency by taking 2 pi divided by the period. Boys find the angular frequency 2 pi times the frequency. On your mark, get set, calculate!
But Mr. Boykin, how do we do that? Don't we have this?
Yeah, we've got
Right.
that data. Girls, who's faster, girls or boys?
Do it, okay? Now, should I do this with them?
Yeah, well, they've got it done by now.
Yeah, they should have it finished, okay? So for angular frequency...
You're a girl, so that'd be 2 pi over the period, and the period is 0.696 seconds per cycle. The next question is, where's the calculator?
Oh, it's on the...
Aha.
over there. Okay, so we got 2 pi divided by 0.696, and I get 9.03.
So the angular velocity, or the angular frequency, is 9.03 radians per second. Sweet. So you guys got this stuff right now. Now, boys, 2 pi times the frequency, did you get 9.03? And the frequency was 1.44 cycles per second.
Okay.
It better be the same.
Okay,
Or physics will collapse.
times 1.44, and we get the same number. Woohoo! Okay, it's my rounding. I rounded here a bit, so I got 9.004, but same idea.
Yeah.
All right, we'll call it the same thing. And again, we get radians per second because this is radians and cycles goes away.
Yeah.
Okay. All right, so.
We've already done the next slide.
Oh yeah. What is the angular frequency? There it is. Okay. Okay, so let me actually let me write that in here. Do we need that for later?
Yeah.
Remember.
So
So
the angular frequency, 9.04 radians per second.
a sec. Okay, I can't remember if we need it later or not, so we'll just write it on there.
Okay, we're gonna need to erase all this and start on the left.
Okay,
Whoa.
so did I go one too far here?
Yeah.
There we go. That's what we want.
So we're gonna sketch a vertical line that's gonna represent the position of the mass as it goes from the bottom to the top. And remember, from the bottom to the top, we got equilibrium there in the middle.
All the way over here.
So label the top, the bottom, equilibrium, and amplitude. So here's the top.
Okay. What would be my amplitude?
Amplitude is the maximum displacement from equilibrium. So you've got 2 of them there. And what was our amplitude? It was
3.2?
3.2 centimeters. So you could just put that like,
I'm gonna go 4.
you can put it down there on the bottom. A equals 3.2 centimeters. All right. Okay, so
All right, next slide. Mark equilibrium as 0. So this right here would be 0. And mark the top as a positive and a negative. Okay,
Yep.
which just means that that's negative 3.2 and that is positive 3.2.
I like that.
Sweet. Okay.
So in your notes, you're doing the same thing. You got the line, and we're going to go through a series of challenges.
Okay, a whole cycle could start at the bottom, go to the top, and come back to the bottom, right?
Yeah.
So it go whoop, whoop, right?
Yeah, a cycle is like clapping your hands. Well, no, that's just, you know, you clap.
Oh, yeah.
Yes.
Let your line, oh, okay, so here's where we're going with this. Let your line that we draw here represent half a cycle starting at the bottom going up. So we're going to pretend.
So a full cycle starts here and goes up and down. Half a cycle would start at the bottom and end at the top. So a full cycle is up and down. Half a cycle is up. That's what we're looking at.
That's what we're looking at here, okay? So for the next few graphs that we write, that we draw, that we create, we're only thinking about half a cycle.
So this is half a cycle right here.
So
Why don't you write half a cycle there on the very top?
that's important. Half a cycle.
All right.
Okay. All right. Here is where we start.
Sketch the line on a position versus time graph. Remember in the video yesterday, they had the thing going up and down.
Yeah. So here we go.
So the vertical, that's too long.
Too long?
Yeah.
I was like, how much?
You're gonna run out of space. There you go.
There we go.
All right, so the vertical is position, and that's time.
Okay.
So at the start, it's at the bottom, right?
Yeah. So
bottom.
right here, it's at the bottom.
No. The
Oh, sorry.
bottom. Look at your line on the left.
Oh, right here, down
Yeah.
at the bottom here. Okay. So at the bottom. Oh yeah, this is my position right here. Okay.
Yeah.
So at the very beginning, it's at the bottom, right? And then as we go through,
There you go.
okay, as we go to the top, as time passes, it goes to the top.
Yep.
Okay. So this is the bottom.
That's the top.
That's the top right there.
And that's
okay.
through half a cycle.
Mm-hmm.
So on the left, we've got the straight line, which is half a cycle. But then we've got time going by. This is also half a cycle.
Yeah, so as time goes by, location starts at the bottom, and then it just goes
Passes through equilibrium on the way to the top. Okay.
up.
You got a sketch of that?
Boop-a-doo. What happens to the velocity of the mass on a spring as it oscillates through half a cycle? Label the fastest, 0, speeding up and slowing down.
Well, where would the speed be 0?
Okay, well, it was 0 at equilibrium, right? Oh, sorry, no. It's 0 at the top and the bottom, right?
Yeah. What happened to that ruler I had out?
Where'd you put? Oh, it's right there.
No, I had a
No?
bigger ruler.
Oh, it's right
Oh, they're right there. Okay. Because what does the slope on a position versus time graph tell us?
Well, the slope of a position versus time graph tells us the velocity.
So what's the slope at the start?
Well, at the very start, the
0, and then
slope
as
is
you
0.
move it along tangent to the line,
The velocity
what's happening to the slope, and then
okay, slowing down right here. So what does that mean then? So that means right here it's getting faster, right?
yeah,
Okay, and then from here to here it's slower.
it's getting slower.
Okay.
And where's it going the fastest?
Well, it's going the fastest right here. Look, because this is 0, this is fast.
Yeah.
Okay, so can we call this V max right here?
I call that Vmax.
Okay, V max. And this is, oh, I forgot again, this is at equilibrium. You can
Yeah.
add that. Muscles. Okay, equilibrium right there. Okay, what else we got?
Where is it going the 0?
So it's going 0 right here, and it's going 0 up there. And that's where it's going the slowest. And this is where it's slowing down, and this is where it's going faster.
Yeah.
Is this making sense? Okay.
Yeah, remember what we're talking about is this thing.
Okay,
Got
moving
it.
on to our next one. So starting at the bottom of a half cycle, sketch the line on a velocity versus time graph.
What is that one? Look at your thing here. Do we
Oh, yeah.
want?
Oh yeah, so we just did the same thing right here.
Except we don't. No. It's this one.
Yeah, yeah.
Well,
you don't want the bottom part?
it never had.
You don't want the bottom part?
Well, no, we don't want the bottom part
Okay.
because the velocity.
Hope you're doing this in pencil, ladies and gentlemen. Okay, so here we go. I remember when you were drawing it.
It was an L.
Yeah.
Okay, so we got velocity on the vertical.
Velocity versus time graph. Okay, and again, so let's go ahead and think about this. So at the very bottom,
At time 0 over in your middle graph there.
yeah, at the wait, was that again?
On that graph.
At time equals
No, time 0 is.
time 0 right here.
Yeah.
Okay. We are going how
0.
fast? 0, right? And well, tell me about the equilibrium here. This is where it's at equilibrium.
That's a maximum
And
velocity.
it's the maximum. Okay, so that means
gonna be
we'll go
up
right there. Okay, and then when it goes, so at the beginning it's at 0. At max it's here, and then what happens again at the top? It's at.
It goes back to 0.
So it looks like we're gonna have something like this.
All right.
Where this right here is Vmax. Okay. And this is the bottom. And this is the top. And this is our equilibrium.
And that bottom line is velocity 0.
Yes. Yeah, let me add that in here. Okay, so I'll just go.
Well, just label the line as 0.
Yeah. Oh, I see what you're saying. Well, right here.
Yeah.
0, right? Okay. So that makes sense.
All right. How we doing? You guys following along as we're doing this?
Okay. Vmax happens. Oh, thank you, Swallow. Vmax happens as the mass passes the equilibrium point. We just showed that.
Yeah.
Vmax equals the amplitude times the angular frequency.
So we could calculate the velocity max
Good.
based on our data.
So go ahead and start doing that, ladies and gentlemen. I'm going to go ahead and do that right under here. So Vmax.
And the amplitude is 3.2 centimeters.
Okay.
And the angular frequency, did we do that?
Yeah, we put it right there.
Oh yeah, 9.04 radians per second. So this will give us a velocity in centimeters per second, which is fine. That's still a velocity.
Okay, so we got 3 point on. Okay, we got 3.2 times 9.04, and I get we'll call it 28.9.
So 21 centimeters per second is the maximum velocity in the center. And going up, it speeds up to that maximum velocity. Once it passes equilibrium, it slows down to 0 again.
Yeah.
Sweet.
Okay. Let's go to our next one here. Okay. So why is this the fastest point? So why is it the fastest point at that equilibrium mark?
We need to ask a few questions to answer this.
What happens to the restoring force as the mass oscillates?
Oh.
What happens to the restoring force as
Well,
the mass oscillates?
Over here, what does equilibrium mean?
Well, equilibrium means where the net forces all cancel out. Acceleration is 0.
Yeah.
Right? And so when we have the spring stretching down to the bottom, the only thing that I can think about is being pulled back
Yeah,
up.
the restoring force
Right?
trying to restore equilibrium, so
Okay.
that force is up.
Okay, this way. Is that
Yeah, put an F on it.
okay?
F sub R.
So this is our restoring force, okay?
And then when it's above equilibrium,
Okay, again, I'm going to go ahead and just draw it all the way. Okay, it's trying to restore it this way,
yeah.
right?
Yep.
So the reason that it's the fastest at this point right here is because that restoring force is pulling it back there, and it wants to get there
Slow
as
it
fast
down.
as possible. Yeah.
See, the restoring force on the bottom makes it go faster.
Mm-hmm.
And then the restoring force after it passes equilibrium makes it go slower.
Mm-hmm. Faster.
We making sense here?
Okay. All right. And what's next here? Where would the restoring force be the greatest, the least? Well, our restoring force would be the greatest right here, and
F max positive.
oh yeah, let me put that. I like it like that better. So
F max positive, or positive F max.
oh, this down here is yeah,
Because
positive.
it's pulling up.
Oh. Man, what is wrong with me today? Positive F max. Okay, positive because pulling up this way.
Yeah, and then at the top it'd be positive or negative F max.
Sweet.
All right.
Okay.
And in the middle,
It would be 0.
0, right?
Right? You guys should add that in there, okay? Sketch a net force versus position graph for half a cycle from bottom to top.
What does that look like on your cheat sheet?
Yeah, so for this one, okay, we did the whole thing. Looks something like this.
I think you can erase that green stuff. It
Yeah.
might get in the way.
You guys have that written down?
Oh, yeah.
Oh yeah, we're writing
You're
everything
doing all
down.
this in your notes as you go along, right?
Okay, so I'm doing. Okay, when I first did this one,
Okay, this is force,
and this is position.
position. And
not
let's
time.
put force 0 in the middle.
Oh, right,
No,
right here.
yeah, on that line, that's going to be 0.
And then force max.
Force max. And that would be negative right there, yes?
Yeah, yeah.
And then at the top, force max, positive.
Okay.
Okay.
And so this is not time, this is position. So
Yeah, what we've done is we've taken this and turned it on its side and put it right there.
So we're gonna call this the bottom, and this the equilibrium, and this the top. Okay.
All right, so what would the graph of the force look like? Well, at the bottom, what's the direction of the force?
Well, at the bottom it's positive. It's a positive F max,
So
and
we're
it's
gonna
going towards 0.
So we're going to start up.
Okay. So at the at the bottom, okay, at the bottom it's going to be a positive F max.
It's pulling up.
Yeah, and then over here you see at the equilibrium we're going to 0 from our net force.
Now it's pulling down.
Okay, and you know what? Okay, 0 right there. Okay, and then at this point now the spring is gonna look. Oh, that's kind of crooked.
That's all right.
Okay.
It's a sketch.
Yeah, make it look better than mine. Okay. And then as we go along, at the top, it's gonna be a negative F max again because that restoring force is pulling in. Okay?
Now notice we've got 4 different representations of what's going on with this thing. We've got just a one-dimensional up and down. We've got a position versus time. We have a velocity versus time, and now we have a force versus time. And all of this is giving us information about what's going on here.
Okay. And I think on our next slide we have something else about this. What about the acceleration of the mass as it oscillates?
And if you want a hint.
Okay, so force equals mass times the acceleration. Our mass here is constant. So whatever our force is positive here, which means our acceleration is going to be positive, right?
Yeah, that means it's up.
Mm-hmm. And down here, our force is negative, so that means our acceleration is going to be negative. And how does that manifest itself over here?
Well, now let's look at the first one on the far left.
Mm-hmm. So as the mass in the spring is extended down here to its maximum, its amplitude here, and when it goes back, when the restoring force is forcing it back this way, that's when it's going to be it's speeding up, right? It's going faster.
Oh, you know what just occurs to me? What's the slope on a velocity versus time graph?
Velocity versus time graph, the acceleration.
The acceleration. So what happens to the tangent of the line?
Okay. Oh my gosh. Good. Okay. So acceleration is fastest. Slowing. Acceleration is now 0.
0 in the middle because the net force is 0.
Mm-hmm. And now now the acceleration is increasing as from here as well, but in the negative direction.
And why is it increasing? Because the force is increasing.
Mm-hmm. And when we say it's increasing in the negative direction, the speed is increasing, but it's slowing down.
Right.
Okay, that's why it's the negative direction.
So once again, let's go back to our oscillating mass. Mm-hmm. There's a lot of stuff going on here as it goes up and down. Yeah. And so we're trying to reach a greater understanding of what's going on.
And one thing you could do I think, like, I don't know if this is something you do with the kids, but you could challenge yourself. You know, talk yourself through what is happening to the velocity at every single point.
Yep.
What is happening to the acceleration? What is happening to the force?
Yep.
Is that everything we got in there?
Yep.
Yeah.
Well, and it starts with position, because it's really just going up and down, right? And so we're representing what's happening by different graphs. Here we've got the position versus time. As time goes by, the position goes like that. what's happening to the velocity as time goes by. It looks like that. But what happens to the force versus position? And so this leads us to acceleration, which is the slope of the middle line, as Ms. Moore greatly pointed out.
Wrong one. Okay, what determines how fast the spring went up and down? Why? Okay, well, here is our spring.
Okay, you take a mass off.
I'm taking a mass off. Oh, this was 200 kilograms.
Oh, well.
That's right. It is what it is.
It is what it is.
So, so I've got 100 grams on here, and it's going dink,
Faster.
dink, 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 dink. Okay,
Dink,
and I'm gonna go
dink,
ahead and change
dink,
the
dink,
mass.
Dink, 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 dink,
Dink, dink, dink.
It's slower.
It's slower, okay. So the mass is one thing that determines how fast the spring goes.
Because of inertia, right?
Yeah, and then we've got the spring
Why is this one
constant.
going faster?
Also my left hand. I don't have the same skizzles. You see how it's like bobbing back and forth. This one's going faster than this one is. And why? Well, it has to do with the spring constant.
The spring is a stiffer spring. That's a weaker spring.
There we go.
Yeah. All right.
Still awesome. Okay. All right. And what's on my next slide? Oh, I just went over there and clicked open something. There we go. Okay. All right. So, so for homework, we're gonna add something. Oh yeah. I forgot to put it in there. For homework, you're gonna do page 275.
It's 275.
Number 18. Ooh.
It's a graph, and those are not multiple choice. A, B, C, D.
Woo! We love doing homework. Okay. Go for it.